Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are doing a deep dive into the Bohr model of the hydrogen atom from Unit 12, Atoms. This is one of those conceptually tricky topics in modern physics, but we'll break it down so simply, so clearly, that you will not only lose all fear, but will be fully ready for those board exam questions. So let's start with a bit of a mystery. Tell me, have you ever looked at those glowing neon signs that shine bright red?
Yes, of course.
Or maybe you've seen a chemistry lab experiment where sprinkling salt in a flame turns it a bright yellow.
That's a great question. I always just thought it was because they were very, very hot,
Right,
like how a piece of iron glows red when you heat it. I
right.
just assumed the temperature was what decided the color.
And that is the surprising part. It's a very common idea, but it's actually what drove physicists crazy back then. Temperature, you see, it affects how bright the light is, the intensity.
Okay.
But the specific color, the exact wavelength, that's not about temperature at all.
Wait, really? So if I heat sodium, it's always going to glow yellow, whether it's super hot or just, mildly warm.
Exactly. That yellow is sodium's unique fingerprint of light. It's like its calling card. And every element has one.
A fingerprint of light. I like that.
That fingerprint tells you something really deep about the atomic structure itself. And in classical physics, it had absolutely no way to explain why sodium gives yellow light and neon gives red.
So that's where Bohr comes in.
That failure is what led directly to Niels Bohr's revolutionary model. Okay, so let's unpack this crisis first. Before Bohr, we had Rutherford's model. You remember that one, the planetary one?
Yes, a tiny positive nucleus at the center with electrons orbiting it, like planets around the sun.
Brilliant model, but it created a massive problem almost immediately. A contradiction that, well, it threatened the stability of the entire universe.
You mean the stability problem, right? Where the electron is supposed to fall into the nucleus.
Precisely. See, according to Maxwell's classical theory of electromagnetism, which was rock solid, mind you, any charge that is accelerating must constantly emit electromagnetic radiation. It has to lose energy.
Okay, and an orbiting electron is always accelerating because its direction is changing.
You've got it. So if that orbiting electron is constantly radiating energy, what happens next?
It loses energy, so its orbit gets smaller, and it spirals inwards,
And crashes straight into the nucleus.
so the atom just collapses. But how fast would that happen?
The numbers are just staggering. Calculations showed that the atom should collapse almost instantly. It would finish its spiral and self-destruct in about 10 to the power of minus 11 seconds.
That's unbelievably fast, faster than a blink. So everything should have just vanished ages ago.
Exactly. But clearly atoms are stable. They last for billions of years. So the only possible conclusion was that the classical laws, they just fail at the atomic scale.
The old rules don't apply.
They completely break down. And the solution came from Niels Bohr, who took up Planck's radical idea of quantization. The core idea is this. Electrons don't have the freedom to orbit at any random distance. They can't be just anywhere.
Okay.
Instead, they can only occupy certain special orbits, special lanes, you could say, and each lane has a specific fixed energy level. Let's use the parking garage model to make a mental image. Think of electrons as cars. Now, a car can only park on level 1, or level 2, or level 3, and so on.
And it can never be between levels.
Right.
I can't just leave my car floating halfway between level 1 and level 2.
You can't. Those discrete levels, level 1, level 2, those are the only allowed energy states for the electron. And this is what quantization means. It's not a smooth ramp. It's a set of distinct steps.
And this solves the collapse problem.
It does, immediately. The lowest level, n equals 1, that's the electron's favorite spot. It's called the ground state.
I see. And since there is no level 0 or any lower orbit available, the electron can't spiral any further down. It's stuck.
Precisely. It's locked in the ground state. And because it can't fall any lower, it just stops radiating energy while it's in that orbit. Stability is restored.
Wow. So he just declared that the old rules don't apply in these special orbits.
He did. These discrete orbits are like rungs on a ladder. The electron must be on a rung, never between them. So, now that we have the basic idea, let's look at the 3 formal postulates he proposed. These are the rules you have to know perfectly for your exams. The first one was all about these stable orbits. Could you please read Bohr's first postulate exactly as it is in the Ansert textbook?
Yes. It says, Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy, contrary to the predictions of electromagnetic theory. These are called the stationary states of the atom.
See, That's a direct challenge to classical physics. He's just saying, in these special stationary states, even though the electron is accelerating, it simply does not radiate. That break from the old rules is what saves the atom. So the next question is, how did he define which orbits are allowed? He needed a mathematical rule for it. That's postulate 2. Could you read that one for us?
Okay. Bohr's second postulate defines these stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h divided by 2 pi, where h is the Planck's constant. Thus, the angular momentum L of the orbiting electron is quantized. That is, L equals nh by 2 pi.
And here is the magic key. Angular momentum, L, can only come in these fixed packets, these multiples of h by 2 pi. The number n there is the principal quantum number. It can be 1, 2, 3, and so on.
But why that specific value? I mean, h divided by 2 pi, it seems a bit arbitrary. Did he have a reason for it back then?
That's a brilliant question. And the honest answer is, at the time, no. He admitted it was basically a guess or rule he had to invent to make the math fit the experimental data for hydrogen.
So he just postulated it.
He had to. But here is the amazing result. Because L is quantized, it mathematically forces the radius of the orbit, and more importantly, the energy of the orbit, to also be quantized. When he worked through the math, this formula for the allowed energy levels just popped out. N equals minus 13.6 electron volts divided by n squared.
And that matched experiments.
It matched perfectly. For the ground state, where n equals 1, the energy is minus 13.6 eV. This was exactly the measured ionization energy of hydrogen. It was stunning proof that his guess was somehow correct. Now for the final piece. If electrons don't radiate in their stable orbits, how do we get those atomic fingerprints? How is light actually produced? That's postulate 3.
Insert states. Bohr's third postulate states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted, having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by h nu equals E initial minus E final.
And this is it. This is the mechanism. An electron gets excited, maybe you heat it up, and it jumps to a higher unstable energy level. Then it quickly falls back down to a more stable one.
And that fall is when the light is created.
It's only during that jump between the discrete levels that it radiates, releasing the exact energy difference as a single packet of light a photon. Hope everything is clear so far. This concept explainer is from ProfSam.com.
So this third postulate is why we see those sharp lines in the spectrum. Because the energy levels E and F are discrete, the difference between them, that delta E, is also discrete.
So you only get specific energy packets being released, which means only specific wavelength or specific colors can be emitted. And there they are, the unique atomic fingerprints. Let's take one quick fantastic example. The visible light from hydrogen is called the Balmer series. This happens when electrons fall down to the n equals 2 energy level.
Okay.
So if an electron falls from the n equals 3 state down to n equals 2, the energy difference is about 1.89 electron volts.
And that energy corresponds to a specific color.
Right. Absolutely. When we use a formula to calculate the wavelength of the photon that this jump produces, we get exactly 658 nanometers. Do you know what color that is?
Oh, right.
A bright, deep red light. This is the famous H-alpha line, the most visible line in the hydrogen spectrum. The fact that Bohr's theory could predict this exact color was the proof that he was on the right track. Now let's go back to your brilliant question from earlier. Why must angular momentum be quantized as n times h by 2 pi?
Right, the arbitrary rule.
Bohr couldn't answer it, but the explanation came later from Louis de Broglie. This is where the electron's wave nature comes in.
De Broglie's idea that electrons are both particles and waves.
Correct. De Broglie figured out that Bohr's special orbits are simply the ones where the electron's wave can form a stable, standing wave pattern around the nucleus.
Like a guitar string.
Exactly like a guitar string. For a stable vibration, the length of the string has to fit an integer number of half-wave lengths. It can be 1 loop, 2 loops, 3 loops. It can't be 1.5 loops, or the wave just cancels itself out.
I see. So for the electron's wave, the circumference of its orbit must fit a whole number of its wavelengths.
Precisely. The circumference, 2p par, must equal n times lambda, where n is an integer. And when you combine this condition with de Broglie's wavelength formula, you mathematically derive Bohr's second postulate.
Wow. So Bohr's guess wasn't a guess after all.
It turned out to be just basic wave geometry. The integer n is just counting how many full wavelengths fit perfectly into the orbit. It beautifully connects everything together. Okay, now let's talk about two crucial misconceptions. The silent killers that can cost you marks in your exams. Misconception 1. This is the biggest one. Many students still picture electrons as little planets that, when they lose energy, they sort of gradually spiral or slide from one orbit to another.
Ah, so I should never use words like slide or gradually.
Never. That's classical thinking. If they could slide, atoms would collapse. The reality of the quantum world is the jump.
A discrete transition.
Yes, an instantaneous quantum jump. The electron literally vanishes from the initial state and reappears in the final state without ever existing in between. Always use jump or transition. Misconception 2. Some students think Bohr's model works for all atoms, for oxygen or carbon. This is wrong.
Right, you said it was for hydrogen, so it's only for hydrogenic atoms.
What does that mean, hydrogenic?
Atoms with just one electron. So hydrogen itself, or maybe singly ionized helium, He plus.
Perfect. Or doubly ionized lithium. It only works for single electron systems. The moment you have 2 or more electrons, you get electron-electron repulsion, and Bohr's simple model just can't handle that complexity. So remember, Bohr model means hydrogen-like systems only. Now, to lock this all in, here are 2 memory anchors. First, a phrase to remember. Quantization saves atoms. Without discrete levels, everything collapses instantly.
Okay, that's powerful.
And second, a physical gesture. Imagine you are climbing a staircase. Step firmly from one step to the next.
Okay.
Now, try to press your foot down and stand smoothly between 2 steps. You can't, can you?
No, it's impossible.
That physical difficulty is exactly what electrons experience. They must be on an energy level they cannot be between them. That is quantization. So, to summarize, here are 3 exam-safe facts about the Bohr model. First, Bohr solved the atomic stability crisis. He did this by postulating stationary orbits where electrons do not radiate energy continuously, which directly contradicted classical physics. Second, the orbits and energy levels are quantized. This is enforced by the rule that angular momentum must be L equals nh by 2 pi, which then leads to the accurate energy formula N equals minus 13.6 eV by N squared for hydrogen. Third, the model brilliantly predicts the specific wavelengths of light that are emitted when electrons make instantaneous jumps between these discrete levels, perfectly explaining the colors of the hydrogen line spectrum. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Thank you for diving deep into the quantum world with us today.